Okay, it's my great pleasure to be here and provide this my thought on this quantum control, quantum simulation with co-atom molecules. I understand this is good. It's a new research institute on quantum information, supported by Hong Hai. Okay, I'm very glad to hear this, see this new development, and hopefully we'll find some kind of this common ground. Okay, to share information and perhaps future collaboration. My name is Cheng. I'm originally from Taiwan, and Dr. Lin Junda mentioned, okay, I graduated from National Taiwan University and we've been working at University of Chicago in the past about 15 years. Okay, all right. So what you see here is Chicago downtown, okay, and our university not far from downtown, about 15 minutes driving distance. Okay. And I took this particular kind of a view of our campus to show it's a recent development. Sorry. Okay. It supported by the National Quantum Initiative. We have the Chicago Quantum Exchange. Okay. And I will talk about the activities here and the role the researchers are playing. Okay. And also the engineering faculty members collaborating on various different this direction of quantum science and quantum engineering. Okay, so as mentioned in these quantum centers, okay, and you can see this is a map. Let me see, I need to turn on the laser pointer. Okay, and Chicago here in Illinois. Okay, you might know in the past 2 years, there's a major effort to support quantum research, and including the research university in the U.S. as well as the national lab. In particular, we have you can see the green ones are the national lab. It's a new quantum research center supported by DOE, Department of Energy, and the blue ones are the ones supported by NSF, okay, National Science Foundation. In particular, in Illinois, we have 4 centers, okay? And they are all so kind of connected with University of Chicago in different ways. And we do have this our Argonne National Lab, okay, is leading the so-called this next generation quantum science engineering in collaboration with our university. Okay. And also Fermi Lab, which is also not far from, is all very close to our campus. Okay, tools supported by DOE on the superconducting quantum materials and the systems. Okay, and also the other 2 center more focused on fundamental kind of aspect of quantum science and engineering. One is a hybrid quantum architecture and networks led by University of Illinois in Urbana-Champaign, and also another one from our chemistry department into quantum sensing for biophysics and bioengineering. So you see, there's a lot of this. All this happened in the past 2 years, okay? And toward the end, I'll tell a bit more about how we are involved, okay, at the university, okay, associated with these centers. So this is a very exciting era. Okay, I'm very happy people start to stand their focus to quantum engineering and try to challenge its the major effort toward this quantum information control and the quantum computation. Okay, and you can see our the website Chicago Quantum Exchange. You can see all kind of activities here, and also this is 4th year they have a kind of Chicago Quantum Summit, okay, to collect talents and also industrial collaborators to share progress, information, and the future collaboration plans. Okay. All right, so that's a short kind of advertisement in the beginning. So I'm going to, in this talk, I hope I can just, there are a lot to cover. Okay, this is a very active, vibrant area, reaching out to every corner in science, this physics, chemistry, engineering, and so on. So I try to give you a kind of broad overview. Okay, first on what is quantum information? Why do people put so much hope that quantum information processing can do better than classical? Second, that's one of the point that's highly debated. Okay, what would be the best qubit to be processing the information, and what are the challenges ahead? Okay, And what are the near term meaning, say 1 year or 2 years, what are the near term application we can expect, and what will be the longer term application we hope we can achieve. Okay. And lastly, I'll come back to show how quantum exchanges show you about the activities we have on campus, and also connection to national lab and partially to industrial world. Okay, so focus on the first. I think that audience, probably many of them have taken this college, this physics. Okay, the first one of the essential concept in quantum physics, okay, is so-called superposition principle. And the superposition principle, it turns out, can be a classical phenomenon. Okay, so this is one of the famous experiments that really tell us a lot about how particles works in a most fundamental way. Okay. Called double slit experiment, when you turn on the light and the 2 slits are open, okay, then the light can go through. If you only open 1 slit, then you'll see pretty much this bright spot on the screen. However, when you turn on both of them, you do not see just 2 bright spots. You also see this interference pattern. Okay. In some location, you have no light. Okay. It's that you open 2 doors, and then in some location in the room, then you see nobody's coming. In some other location, you're in the room, you see there's a higher probability, okay, to see people come to the same location. So in the classical system, this is understood in terms of the addition of electric field. Okay, and when we add 2 electric field can be described by a vector. They can cancel. In some location, they distract interfere. Some location contract interfere. Okay. That's how we understand why in some location, okay, even with 2 kind of slits open, there's no light going to that location. But the funny thing is that the same experiment also works on particles. Okay, and even if you send individual particles, so when you open 1 slit, say that consider here electron, assuming my laser pointer is electron. Okay, in some location you see this, you can see the finite probability that electron can arrive at the screen. However, when you open 2 slits, okay, to certain location you see a distract interference. Okay, while classically you consider the probability should be doubled. Okay, it's like you open 2 windows and turns out there's no air going into the room. When you open 1 window, there's air coming in. That's weird. Okay, so on a very fundamental level, we realize, okay, even the dynamics or this distribution of particles should be described by quantum mechanics. And we're using the wave function in the way similar to electric field. There is some kind of field associated with the particle that can add, that can subtract. The probability is not the sum of individual probabilities, but the sum of the fields. Okay, and this is called wave function, and that allows us to understand this why there's also interference pattern. And the experimental proof can be seen if you send individual particle to 2 slits. Okay, then you can see each particle register on the screen. Right? You perform, if you integrate for long enough time, okay, then this interference pattern is very clear. So this double slit experiment shows a very important nature of this quantum mechanics. That, okay, well, classical system, either the particle arrive at the location, not arrive at the location, described by classical probability. In quantum mechanics, described by some kind of this we call wave function, and that wave function can be superimposed. Okay. The particle can have a certain amplitude to arrive at the screen, and also some amplitude arrive to not arrive at the screen. Okay. So this is a fundamental difference between how we treat the information in classical way and quantum mechanical way. I think you probably see this slide in probably many talks. I want to go a little bit deeper, okay, to show you there's a even deeper difference between the two. Classical information fundamentally is continuous. Okay, the digitization is coming from our own definition. We define 5 volt as on and 0 volt as off, and so on. But quantum mechanically, what quantum is, this particle or photons and so on, they are quantized. If either you see 0 atom or you see 1 atom. Okay. So on the most fundamental level, okay, supposedly this digital signal processing should favor quantum mechanics because the signal naturally kind of discrete. Okay. Our detectors sometimes do not see a kind of perfect discrete. Okay, here you can see our experiment, we can see individual atoms. Okay. If you sum over, if you build a histogram, you see when there's when the pixel when you have no atom, you have one distribution. The one atom, another distribution. The distribution seems to be analog, seems to be continuous, and this is actually coming from our detection noise, coming from the noise of the camera, okay, or the noise of the photon. Fundamentally, quantum signal should be discrete because energy in terms of this discretized unit. Atoms also 0, 1, there's no 0.5 atom. Okay. So on fundamental level, you will think it's natural to think about digital signal processing with a quantum system. Okay. Second, let's talk about now. If you really say this, the system is described by the wave function, it turns out evolution of the system, you can just see how this wave function evolve with time. And then we learn from quantum mechanics, there are two simple rules. One is that because we can treat this wave function as a vector, okay, just like what we learned in kind of this high school. Okay. It's a vector. That means that you can choose the origin, the vector is in a particular direction, okay. And then the way system evolve can be fully described just by a rotation of the vector. Okay. So how the system going from this, you can consider this in the beginning, you put in your information into the particles, and the particle can be described by your initial wave function c at t equals 0. As the time evolving, for example, during this time, you want to do some processing. Okay, if this is a quantum computer, you put in an input, then you hope the output, okay, that's a wave function at later time, can reveal the answer of the question that you put into the system in the beginning. Okay, so we have this idea to use the evolution of the system, okay, to solve problem, just like how you put in the just like how this we do any signal processing or trying to solve a problem with a classical computer. All right, so the first rule is that this vector is very simple. Fundamentally, it looks very simple. Here we say the length of the vector is always 1. This is coming from probability conservation. Okay, the number of particles, at least for the kind of a quantum mechanics we're talking about here, they never increase or decrease. Second, the evolution follows a linear algebra. Okay, so it looks like this very simple linear algebra, meaning so if you have it's a vector, and then all you have to do is perform transformation and get the final state. Okay, so all the physics, all the problem solving, everything can be described by this operator with a linear. Okay, all right. Okay, so applying these two rules, if you have one particle, okay, then the particle can be either on the screen or not on the screen, or you can define any two state. Say the state can be 0 or 1. 0 can refer to say spin down or spin up. 1 can refer to spin up, and so on. Choose any two states, okay. And then if the system either in the state 1 or in state 0, then the probability should sum to 1. Okay, and this amplitude, that's what we discussed earlier. This amplitude square tells you the probability. For 2 qubits, will also be the same. So 2 qubits, then they can they can both, the 2 qubits can both be in the state 0, 0 or 1, 1, 1. Okay, 1 and the first one 0, 1, the second one 0. There are 4 possibilities. Okay, and this C, D, E, F are just the 4 coefficients that tells you the amplitude. And if you take the absolute value square, determine the probability, and the sum of the all probability should be equal to 1. I mean, the system can be found in one of the 4 possible kind of these states. Okay, so that means this is just not a vector, but this time in 4 dimension. So if you learn from kind of high school, okay, so you can choose a vector. Say the vector has 4 elements. I mean, X, Y, Z, okay, and also W. Okay, you can draw 4 kind of principal directions and then describe any point in this 4-dimensional space based on 4 numbers. And this is the case. C, D, E, F are the 4 coefficients that determine location of this vector in this 4-dimensional space. All right. So I mean, the evolution of the system is just a rotational vector because we know this the system is the absolute value is 1. It's all this on the surface of the sphere. It's just a high dimensional sphere. Okay, since it's always on the surface of the sphere, then the evolution of the system is always it's just like it's just a rotation. Okay. In the beginning, you might be here, described by C, D, E, F. Later, it comes there, okay, by another set of 4 numbers, and that's it. Okay. That's how fundamental this how quantum mechanics tell us. Okay, is introduce a vector and the vector will rotate. That's it. Okay. All right. So obviously the complication, all the kind of this computation and so on, algorithm and so on is all included in this U. How do you convert a question into an answer? You can think about the question is something we type. Say on the keyboard, we can type the question. I want to calculate, say 3 multiplied by 5, and then I want to get the answer. And then this solution of quantum system supposed to play the role to do the operation that we want. Okay. Now, what's the difference between classical quantum? Now we said there's a superposition. That is something you do not have in the classical computer. You can think about in a classical computer, you have one question, you send it to the CPU, U is the CPU, and then you get a result. You get a result on the screen. That's how we think classical computation is. But once quantum mechanics allows superposition, okay, you have a superposition many different states. Is that you have and the linear algebra tells us once you have this multiple input, it's just the same operator. You can convert every single input into the corresponding output. Okay, and this is what we learned from linear algebra, right? This is a linear operator. So this is equivalent to have n keyboards. Okay, each keyboard you can put in different different input, and then so it's only one computer. Okay, and then you can get the result. So solving n problem is essentially the same as solving one. Okay, yeah, and as far as this computer is concerned, solving n problem and solving one essentially is the same. Okay, because it's governed by linear algebra. All right, if this is the case, then the potential or the performance of this quantum computer will depend on how many kind of operation the computer can process in parallel. So you can make such a kind of a comparison. Let's assume a small computer with 20 bits. Okay. All right, in classical system, the 20 bit each one will take 0 or 1, so you only need 20 binary number to essentially that you type in. You have say your keyboard has 2 keys, 0 or 1, then you just type 0, 1, 0, 0, 1, and so on. Okay, assuming there's only 20 bits of memory, so you type the keyboard 20 times. Okay. Even with that 20 binary numbers, okay, there are many different ways. Okay, the first time there are 2 possibilities, 0 or 1. Second, there are 0 and 1. So there are 1 million configurations. But every time you can only have 1 keyboard, you can only do it once. Okay, only 1 input at a time. Okay, so quantum mechanics say you can have a superposition. So all these possible configurations can be superimposed together. So you can describe the whole this essentially is that you have this 1 million keyboards. Okay, and each one of them, the first keyboard can type all 0, 0, 0, the second keyboard 0, 0, 0, the last one is 1, and so on. And then you can get a great superposition and send it to a computer, and the computer will solve it. Okay, it's also just one operation that the classical computer solve all the problems. Okay, all right. So to really describe this the system, okay, now we realize, okay, the state is described by 1 million coefficients. A1 is a coefficient. Just like a linear algebra, you choose a basis. Okay, you have all the coefficients you can choose. There are 1 million coefficients. Okay, let's assume for simplicity, each coefficient can take the value of 1 and -1. So each coefficient can take 2 values. So therefore, there are 2 to the power of 1 million configurations. Okay, if you think about it, 2 to the power of 1 million is astronomically larger than 2 to the power 20. Okay, so this also means you have essentially 2 to the power 20 keyboards that can be working together, the same in all these configurations, and then to send in this 2 to the power 1 million keyboard to send so that's the number of this superposition we can have given by the number of coefficients. All right, so that is a kind of quantum speed up, okay, going from 1 input at a time to 2 to the power 20 at a time. This also means if you try to increase 1 more qubit, going from 20 to 21, okay, the number of configurations is doubled. So this is different from, say, you buy a USB, okay, from the store, then plug into a computer, then say USB is 1 terabyte, then increase the memory by 1 terabyte. Memory increase by 1 terabyte. However, every bit you put into your quantum computer is supposed to double the performance. We go from 2 to the power 1 million to 2 to the power 1 million 1. That's a factor 2 larger. Okay, so with this a huge possible kind of a superposition, certainly you can imagine one way is that you can essentially perform the search much more efficiently, okay? Because you can essentially try out all the possible this path all at once. Okay? And then if the quantum processor is doing the right job, how does it work? You try to just combine all these paths, and then they will interfere and in the proper way to solve the problem you want. And ideally, the answer will emerge among this qubit by this construct interference. The amplitude become larger and larger. Eventually, the output of the 20 qubits supposed to tell you the answer. And the quantum algorithm is the kind of a theoretical approach, trying to figure out how to kind of evolve the system so you can convert this problem into a solution. Okay, so this is one potential application is in terms of search and optimization, because you can just try out all the possible configurations at once. Another very important application that people realize is about factorization. Okay. Here I'm showing you a number and the n, and we know it's a product of 2 primes. And now our test is trying to determine the prime. If you know one, then immediately know another one. But what you get is this large number. This is about 250 digits. Okay. This problem was proposed about 20 years ago, and it was factored last year. Okay. And this problem is proposed by this RSI. This is a cybersecurity company. Okay, because nowadays the cyber communication security is heavily based on this the impossibility to factorize a large number. Okay, all right. So you see, and that's a current limit. They propose a whole bunch of large numbers. Also, the next number 260 digits. The next one 275 digits, and none of those has been factored out. Okay, and this after many years effort. Now the solution right here. You can check the solution easily. Okay, you can just put it into the computer. Okay, if you know the primes, you can double check. You can verify it did. This number multiplied that number will give you the original number. You can probably this calculation probably take a second. However, if given the product, you want to determine the kind of cofactors, and then this is a extremely difficult job. Okay, and 250 digits is pretty much the limit of our classical computation. And it was Peter Shor in the 1994 to show that if we can do if we do have a kind of a powerful enough quantum computer to do this, okay, just by this linear algebra that we discuss, okay, you can speed up the processing time, essentially by a factor 2 to the power 250. Okay. All right, and you can imagine, you can calculate how large that number is. All right, but people did a calculation. I'll show you the result. So this is the binary length of the number people can factor, okay? And no, none of the people can factor. So people can estimate how long it will take. If the number is only 64 bit, okay, the supercomputer can factor it out in kind of a small fraction of picosecond. Okay? But very quickly, the problem becomes intractable. Only 512 bit, it will take an hour. You go to 2000 bit, I think that's currently the the number of digits people use, okay, to ensure that this ensure that this internet security. With 2000 bit, according to this scaling, the classical computer, look at the open circle, the classical computer will have to take 10 to the 15 hours, okay, to solve the problem. However, with the quantum computer, even we do expect quantum computer might not be as fast as a kind of the best classical computer. However, because of this great parallel calculation, this enormous capacity to process all the possible input at once, the Peter show that there is essentially a polynomial power law type of dependence. Okay. At some point, when you reach the kind of 512 digits, okay, then you can start to see the power or the quantum speed up. Okay, the quantum computer, even operating at much lower clock rate, okay, can solve the problem much faster. Okay, so this is why people are talking about a few hundred qubits is likely to the kind of a break-even point. Start to see this superior performance of quantum computer compared to classical. All right, so how do we really implement this? Now I kind of move toward this toward experiment. Okay. So this is a few criteria that proposed by DiVincenzo that have been quoted by this almost the entire community for the past 20 years. So the list of the criteria that you need in order to realize kind of a functional quantum computer or functional quantum computation. First, it needs to be scalable. If you realize in only a few qubits, then you need to show that indeed it's possible to scale it up to a larger number of qubits. Second, you need to have a way to initialize, okay, the quantum state of your m qubit to begin with. And then very importantly, this operation need to be coherent. All those superposition, especially those complex number in front of the states, okay, those superposition carry the phase. And those coherence is essential to ensure that this the functionality of quantum computation. Fourth, you also need to identify universal set of quantum gates. Okay, and say theoretically the problem the universal quantum gate have been figured out more than 15 years ago. It's about how well you can implement these gates with high fidelity and also to keep the coherence. Okay. Lastly, you need to have a kind of qubit-specific measurement capabilities that you can perform measurement every single qubit, okay, with high precision. All right, so let's talk about the main challenge here. Okay, I wouldn't go into the detail because certainly there are people are still trying. There are many different platforms being investigated. But essentially, the major problem in this field. You're trying to maintain the coherence when the system is large. The coherence means for two particles is between 0 and 1. Okay? The phase between them is essential. Okay? But remember, once you have more than two particles, more than one particle, now there are many terms. 20 particles, there are 1 million terms. Each term has its own phase. To be able to maintain the phases of all these coefficients become extremely difficult. And this is show what you typically see. There are two kind of this kind of relaxation that's really bad to quantum computation. One is that in the beginning, say you are in state 1, okay, just without anything, the system can relax back to state 0. Okay. If the state 0 has a lower energy than state 1, there's relaxation. Due to the thermal bath, due to the environmental control, okay. So one of the reasons in many kind of experimental platform, you need to go to low enough temperature to eliminate this the dephase or relaxation due to thermal noise. Second is so-called the dephasing. Okay? That is how well this we know and we control the phase between any two terms. Okay? In this case, I consider 1 qubit. Okay, all right. So if you try to monitor, perform measurement on the phase, you can see in many experiments, you see that the longer you wait, then the harder it is to measure the phase. Okay? The system becomes more and more like classical. Okay, and this phase dephasing, okay, typically due to the unwanted interaction with the environment, or either uncontrolled interaction between the qubits and so on. Okay, and these are essentially the kind of the major obstacle in trying to scale up the system. Okay, when a small system only a few phases to maintain, a large system, then the dephasing become fast. Okay, be sensitive to kind of more particles, sensitive to the environmental noise, much more than when you have more particle in the system. So therefore, okay, with a finite lifetime, say I don't have any unit here, say 40 can be 40 seconds. Okay. So within say 40 seconds, you can still maintain the coherence, you can still maintain the quantum nature of the system. Then the figure of merit is how many operations you can really perform, okay, before relaxation or dephasing take over. Okay, all right, and that really sets a kind of a ground to compare kind of a different platforms, okay, compare different different experimental approach. So one way to go beyond this, if it turns out this the dephasing, the fundamental limit, we're always living in there's always noise in the environment. Nobody can really reach zero temperature. Some experiment closer to zero temperature, some experiment need to operate at mini Kelvin, some can go to micro Kelvin, some go to nano Kelvin. There's always some kind of environmental noise. So one way to go beyond this kind of dephasing, okay, is by introducing this error correction. Okay. All right, and the basic idea is that you have the information you want to protect, okay, and that's 1 bit. And for error correction, you need to introduce other qubits. Okay, here called ancillary qubits. Okay, and it turns out there's any error introduced into the qubit that you care. Okay, you can try to perform this essential quantum circuit in order to correct, so eliminate the noise. Okay, and this error correction was implemented in ion trap about 18 years ago. Okay, but to realize this is something that to a much larger system, even to this day, is extremely difficult job. Okay. So fundamentally, there are ways to get around the dephasing and so on, but in practice, okay, a lot of this idea is limited by the sample size. All right, before I move on to this the more experiment-oriented kind of this overview, okay, I'm just going to share a couple of jokes. Okay. All right, here. Developing a quantum computer prototype. So how's the quantum computer prototype coming along? Great. The project exists in a simultaneous state of being both totally successful and not even started. It's a superposition. Another thing that's more fundamentally interesting is that now you see, could come with when you start to have many more particles, we're talking about a more and more complex system. There are also fundamental problems for physicists, okay, maybe biologists, to think about whether a complicated system can really be in some kind of superposition state. Okay, not to mention this is a 1 million coefficient. Let's just consider 2 coefficients. Assuming all the particle in this cat, all the atom in this cat are in some state that will represent the cat is dead. Or all the particle in the other state, okay, that will maintain the kind of the life signature of the cat. So if all the particle in the particular state, the cat is dead, and you can actually maintain the coherence and maintain the superposition of all particle, okay, in 0 and all particle in 1, then that is a so-called the Schrödinger's cat. Okay, you can get superposition the macroscopic object in the 2 distinct states. Is that possible? Okay. At least for something as complicated as a cat, or for any kind of even bacteria, okay, nobody can realize this. However, for macroscopic molecules, say carbon-16, for complex molecule, people can still see some level of quantum coherence. Okay, so it's not impossible. We believe there's no fundamental limit, but it just it's become harder and harder when you try to scale out to more and more complicated system. Okay, so the last joke. Okay, so Schrodinger is not happy with the cat being in the superposition of life and death. Okay, so send it to the vet. Okay, and the nurse come back with the comment, I have good news and the bad news. Okay, also in superposition. Okay, so now let's move on to the experiment platform. So even when I was a student, there will be a lot of ideas being proposed, and a lot of system being considered will be fantastic, okay, for quantum information processing. Okay, here I just list a few. There's an early kind of suggestion based on nonlinear or linear optics using photon to store the information. Photon also has a polarization, can be vertical, horizontal. You can label them 0 and 1. Based on ions, based on NMR with molecules, okay, nuclear magnetic resonance with molecules, based on spins in this silicon, okay, the Josephson junction, quantum dots, these electrons on this liquid surface, quantum computation, qubits, and so on. Okay, so even after 20 years now, you see that we are still debating what is the best. Okay, so you see this is how this how challenging the problem is. Okay, and the different system were different. For example, you see this they can go to different temperature. Okay, and they are sensitive to different kind of noise. The electron was sensitive to the noise coming from the electric field. Okay, photon will not be sensitive to the electric field, and ion can also be sensitive to field, the stray field, and so on. So different systems they have their kind of pros and cons. Okay, all right, but beyond quantum information, beyond quantum computation, I also like to mention it's not like we are out of hope. Okay, to really see some kind of see some progress within our lifetime. Actually, on the just the opposite. Okay, people have also identified other very interesting applications that really use quantum technology, quantum engineering, entanglement, and so on to really make progress in other fields. Okay, I mean beyond computation. One very prominent example you might know in this in LIGO, the gravitational wave detector. Okay, they build a kind of huge interferometer with an arm of 4 kilometers to measure the gravitational wave coming from colliding or spiraling black holes. Okay, and this quantum squeezing, okay, has been applied in order to improve the kind of sensitivity of the LIGO interferometer by about 2 dB. Okay, the 2 dB is not much, but still that's a fatal not even fatal 2. Okay, yeah, that is but you can see a clear improvement in sensitivity. So this is actually another very exciting field, how to use this control, this quantum engineering to improve our way to sense the environment, even sense a signal from the biological tissues. Okay, application into chemistry and biology and quantum sensing. Another one that we have made a lot of progress in the past decades. Okay, say this in collaboration with this Jian Wei-Pan's group from USTC, and earlier he was in Vienna on the Heidelberg. Okay? And in the past couple of years, they demonstrated that you can also use the quantum physics to realize teleportation, to transfer this quantum state from the ground to the satellite, and likely also from satellite back to ground. Okay, and this is a two advantage. One, you can transfer a quantum state without destroying the coherence. Okay, transfer quantum information. And second, it can also be shown that it can be safe, can be kind of can be secure. Okay, can be secure. Okay, through this teleportation process. Lastly, I'd like to mention something that closer to what we're doing. It's called quantum simulation. Okay. Actually, this is closer to the what this Richard Feynman had in mind in the beginning. We know many people consider him to be the kind of founding father of the quantum information. But in his original paper, it's more thinking about if you to use this quantum processing to understand physics, okay, or physical systems. The basic idea is the following statement. Say you assume you have two systems or more. Say you have a system A, B, C. System A is the atom in the lattice. System B is some kind of atom inside the cavity. Okay, system C is some electron in some kind of inside the material. If you somehow you can make two systems such that they share the same form of a Hamiltonian, the Hamiltonian will govern, in quantum mechanics, Hamiltonian govern how the system evolve. Then in principle, they should evolve identically. So it doesn't really matter whether we're talking about atoms, or maybe we're talking about photons, or talking about electrons. If you somehow you can control you can control how they evolve. Okay? The atom can behave like electrons, or ion can behave like say, I don't know what this is, maybe electron in graphene. Okay, or electron can behave like some other physical system. Okay. And so it's only limited by imagination, how we can connect the physics from atomic system to the physics in condensed matter, or even physics, say, or in nuclear physics, and this is the area that is a little. So I'd like to list a couple of examples that we've been doing the past couple of years. So in our experiment, we're based on atoms. Okay, that is confined in the vacuum chamber that can cool down to a very low temperature. Okay. And then we can interact with this atom with the lasers and so on, and we can control how atoms evolve. We control, and to some extent, we can control how atoms evolve such that they can simulate the condition people discuss in nuclear physics. People discuss in cosmology, in condensed matter, okay, even in particle physics. Okay. So there are a series of experiments that we can use atom to simulate the kind of complicated quantum dynamics. Okay, and we are now had the capability, we are on the verge to be able to simulate this very complicated phenomena. Okay, and some also suggest, say, climate change. Okay, maybe one day. Okay. Right. So a short kind of introduction to our this system is based on neutral atoms. Okay, and the experiment set are very similar to ion trapping and photons to induce the necessary quantum operation. Okay. Right. And the advantage of our type of experiment that we can start with many atoms. Actually, maybe a bit too many. These 100,000 atoms. Okay, so this earlier experiment, we do not have the capability to see individual particles because there are just too many of them, difficult to track 100,000 atoms about 10 years ago. Okay, but nonetheless, we know how they evolve. Okay, and then we also understand this some of the fundamentals in this complex quantum system. And he was my former student, Cheng Hong, who is also from Taiwan, okay, who realized that you can potentially simulate the formation of the cosmic microwave background by looking at the dynamics of the atom. Okay. And this is a paper we published a couple of years ago, the quantum simulation, Sakura oscillations with co-atoms. Okay. All right, I'll skip the details. I think I'm not talking to physicists, not everybody in the audience are physicists, but I'll tell you that there are connections between system A and system B. This is also the concept behind this universal quantum computer. It doesn't matter you use ion or superconducting qubit or different or molecules and so on. If they're all functional, then supposedly it should generate the same result. Okay. Another example, more recent example, try to simulate the so-called Hawking unruly radiation, is how to understand the kind of emission of this light near the black hole, the so-called event horizon. Okay. And such kind of experiment is possible to do. We don't have a black hole we can access to perform the experiment. Okay, but the theory had formulated how this kind of emission can occur, at least locally. So we can, so with my former student, postdoc, okay, we also realized that we can control this atomic system well enough to simulate this Hawking Unruh radiation. Okay, people have been fascinated by the prediction for many years. Okay, here I would also like to show you the new platform we're developing to manipulate atoms in the lattice and to realize universal quantum processor. The basic idea is how we introduce the atoms into optical lattices, and then we use a technique called optical tweezer to rearrange the particle into the pattern we want. For instance, if you have one particle per site in the lattice site, we can use them to store quantum information. So we'll call this qubits. Then we'll use the tweezer to bring some other particle to interact with the qubits, and also to mediate interaction and also entanglement between distant particles. At the end of the day, then the particle will also carry the information to the measurement regime. So you can see more detail about our proposal here. Okay, so now let me move on to the last topic, just to tell you about the other kind of project going on at the University of Chicago under this Chicago Quantum Exchange. All right, so sorry, there's one more slide to is how we're going to implement this. Essentially, we're going to load the atoms into the center, and then we are going to we can look at how atoms are distributed, based on this our imaging system. It's a high resolution objective. And this new platform also allows us to individually control individual atoms based on the so-called digital micromirror device, which is a device that integrates up to about 1 million small micromirrors that can turn it on and off at the time you want. So therefore, you can prepare arbitrary pattern or optical potential to control individual particles and to bring them to the location that you want, and also to induce a necessary kind of interaction between their neighbors. Okay, so now let me move on to the last topic. Also show you about this few kind of center under this National Quantum Initiative that's currently going on, and I'm also personally involved in some of this. In particular, I'd like to just mention about some of the you can see a couple of issues trying to develop the center trying to develop new generation of quantum science engineering platforms, and a new material for superconducting quantum information processing. I'm also involved in this hybrid quantum architecture and networks. I'll tell you about what the idea is. And also the last one about this application of quantum sensing by physical engineering. Okay, so as we discussed, there are multiple ideas, how to develop the best kind of qubits. And the people have studied this in say silicon carbide or atoms, also spin qubits. We have my colleague working on other type of this qubit platform. And say Andrew Cleland here trying to use phonons as a qubit. He recently has a result to show that you can entangle up to 6 phonons. Okay, so the amazing thing about quantum information process is if you can control this well enough, in principle, even based on different quantum platform, the end result should be the same. The same circuit will give you the same final quantum states. However, now if the issue is that we cannot scale up, it's difficult to make the qubit number large enough. Then the next idea we're looking into is that how about we can connect each other? I might have 3 qubits from this nitrogen vacancy center. I might have a few qubits from the atom experiment, and then if we can build a network, we can share the information. And then perhaps storage can be better done with atom, but communication is better done with photons. And then this processing may be better to be realized based on this condensed matter device, say superconducting qubit. And how do we establish a network to connect them, to convert information from one system to another one? And how do we make sure the information will not get lost during this communication, long distance communication? This will be another the important issue we're trying to address. All right, so in the Chicago area, we are now working with our University of Chicago, also working with Argonne National Lab, as well as the Fermi Lab. And then we have established a kind of fiber link as a potential to really kind of distribute entanglement. So we found different buildings within our campus, as well as to the Argonne Lab, and also one day we'll also extend that to Fermi Lab. So the basic idea is to share the entanglement. Photon is the best way to communicate. We'll create, say, entangled photons and deliver one to one lab, another one to the other lab, and then we can swap the entanglement from the photons to the local qubits. All right, so we'll start with a kind of say between two buildings, even two labs. Okay? And once that's realized, we'll try to go to even longer distance. Okay? All right, so let's conclude. I hope in this talk I told you about this the basics of quantum information, and the foundation of it is based on superposition and entanglement. Okay? And there are practical issues we need to handle regarding the decoherence and also how to scale out the system to more qubits. And this is we are it's an extremely vibrant, energetic kind of a research area trying to identify the best approach, okay, to handle these practical issues. And before we see the real practical quantum computer, I would also like to mention that already kind of progress into other applications in quantum metrology, say like quantum teleportation to share information over long distance, and also quantum simulation, the idea to simulate other type of complex quantum phenomena in nature. Okay. And lastly, we have this Chicago Quantum Exchange supported by a few quantum centers, which have this establishing quantum networks, okay, and trying to develop a universal quantum simulator, quantum information processor, okay, to interact with different quantum groups. Okay. All right, with this, thank you for your attention.